guys, so previously we've already completed the group 1, group 17 and also group 18. Okay, so for today we are going to go into period. Alright, so for form 4 you're only going to learn about period 3. Okay, so for period 3 elements, technically you have sodium, right, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine and argon. Okay, so without wasting any time, all right, so please complete the table for the electron arrangement and of course number of shells. Since we are talking about period 3, right, meaning that the number of shells will be 3 shells, meaning from sodium until argon all will have 3 shells. Okay, 3 shells only, period 3. Right, all elements will have 3 shells in period 3. Okay, so first thing we are going to go, oh, why do I have a short back? Oh my god. Okay, so first thing, we are going to go into the physical properties. Now, for this particular chapter, chapter 4, periodic table, there are a lot of trends that you need to know. So, what do you call atomic size, electronegativity, and then the reactivity. Okay, all these are very, very important. Okay, so this is period, so it's going to be slightly different from the one that we learned in groups. All right, so as you can see here, in terms of size across periods, when you go from left to right or from sodium to chlorine, you will notice that your atomic size is actually decreasing. All right, so technically what is happening here, so I'm going to use this to roughly explain. Okay, so if this is your periodic table, and if you can notice that as you go down the group, right, size is actually increasing. Okay, atomic size is increasing. But as you go from period from left to right, okay, your size is actually decreasing. Alright, so the red balls here representing the size. Okay, and sorry, so for groups, you know that the size is increasing because as you go down the group, the number of shell increases. But what about period? Why is it that when you go from left to right, the size is decreasing? So this we need to look in terms of the what they call valence electron and also the strength of the nucleus. Now, as you can observe in this part, right, okay, you will see that 281, okay, you have one valence electron right here and then in the nucleus. Now you need to understand that when you go across period, your proton number is increasing, meaning the number of protons in the nucleus is actually increasing as you go across from sodium to chlorine. Therefore, when proton number increases, the nuclei attraction force or the nuclei attractive force is also increasing. So as you can see here in terms of the attractive force between the valence electron and also the nucleus, as you go across from left to right, because the number of valence electron increases, number of protons is also increasing. Therefore, the attractive force is also higher. Now, since you have higher attractive force, meaning that you are going to pull the valence electrons nearer to the nucleus. So as this happens, the size will become smaller because you are pulling the valence electron. As you can see here, the valence electron, this part, all right, are being pulled nearer to the nucleus because the nuclei attraction is actually stronger because you have more protons in the nucleus. Now, since this is period 3, meaning if you look at this one, 281, 284, 288, all will have the same amount of shells, 3 shells. The only difference is that because you have more protons, stronger nuclei attraction, therefore your valence electron will be pulled nearer to the nucleus, hence the size will decrease. Okay, so this is very, very important. All right, for period, size is actually decreasing. Okay, now another part for another trend for period is the electronegativity. All right, so for electronegativity, okay, I'm going to use red. right here. Okay, electronegativity. Now remember, the meaning of electronegativity is that the strength to pull or to attract electrons. Now, as you go down the group, okay, remember size is increasing, right? More difficult to actually pull the electrons. Okay, so as you go down the group, all right, actually your electronegativity is decreasing. Okay, electronegativity is actually decreasing, whereas as you go from left to right, okay, your electronegativity is increasing. Oops, my writing. Electro key thing. Let me just move this. Like electro, okay, negativity is actually higher, all right, or increasing. Okay, meaning from sodium to chlorine. All right, your the power to pull to attract electrons into the atom is actually stronger. So in other words, okay, this one, okay, let me use another color. All right, oops. Okay, so here this is fluorine. In other words, in other words, fluorine can be considered as the most electronegative element. Right, most electronegative element, okay, compared to the others. All right, meaning it is easier or for fluorine to attract or to pull electrons into its atom or nucleus. Okay, so these are the two important what they call trends in the um, periodic table. All right, size go down, group increase, across period decrease, electronegativity, all right, as you go down the group, electronegativity decreases, or in other words, we can also say electropositivity increases. Okay, electropositivity, okay, increases. All right, go across period, the electronegativity increases. Okay, and then we can conclude that we say that fluorine can be considered as the most electronegative element. All right, fluorine. Okay, okay, so that is the trend for atomic radius and also electronegativity. So let's look at the explanation. All right, atomic radius, okay, decreases across period. All right, okay, so they decreases from sodium to chlorine. Okay, why decrease? So this is the explanation. All right, so all atoms of the elements have three shells occupied with electrons. Okay, and then as you can see here, your proton is increasing. Okay, all right, increases by 1 unit from sodium to chlorine. All right, so these three are the important ones. Okay, important points that you need to know when you write for your explanation. All right, increase in proton number causes the number of positive charge to increase. Okay, so this in turn will help to increase the strength of attraction. All right, so the nuclei attraction or the strength of attraction from proton in the nucleus to the valence electron in the shell increases. Okay, hence the size will decrease. All right, decreases across period 3. So this is the explanation. If we ask you to explain why the size of period 3 decreases from sodium to chlorine. Okay, so these are the few important points that you must remember. Alright, okay, so for electronegativity, remember, is increasing. Alright, so remember the strength, okay, the meaning of electronegativity, strength to attract electrons to its nucleus. So why increases? Okay, so these are the 4 points that you need to know, okay, for your explanation. Atomic radius, you always talk about size first. Okay, so atomic radius, okay, decreases. Okay, why decrease? Because the nuclear attraction is strong. Right, so size of atom decreases, so tendency of atoms to attract electron will increase. Okay, because as you are smaller in size, okay, remember when you are smaller in size, the distance between the nucleus to the electrons outside is shorter, so it's easier to pull the electrons. Okay, therefore your electronegativity increases across the period. Okay, so those are the two important trends that you must know. All right, atomic size and also electronegativity. All right, so in terms of physical state, okay, previously we learned that periodic table, left side is metal, right side is non-metal. All right, so technically your physical state is changing from solid to gas. All right, from left to right. Okay, another physical state is this one. Okay, if you notice that all these are metal, okay, semi-metal, we have another meaning for that, and non-metal. Okay, so these are the two physical states of the period tree. All right, so sodium, magnesium, and aluminium, normally we classify them as metal. Okay, silicon is considered as semi-metal, or another word for semi-metal is metalloid. Metalloid. Alright, so remember, if you see the word metalloid, we are actually referring it to semi-metal, whereas from phosphorus to argon are non-metal. Okay, so if you are metal, definitely you are good you have good electrical conductivity. If you are non-metal, meaning you cannot conduct electricity. Okay, semi-metal, technically they are weak, but we can actually increase their conductivity. Alright, so if you see this sentence right here, but increases, okay, with the presence of boron or phosphorus. Okay, so technically I can increase conductivity by doping. Okay, so doping is, the meaning of doping is that I add other elements. All right, so in this in the context of silicon, the meaning of doping is either I add boron or phosphorus into the silicon metal. So when I add these two into the silicon metal, their electrical conductivity will increase. Okay, so this particular process is what we call as doping. All right, this one later you will learn in your physics. Okay, so for melting point and boiling point, all right, if you are metal, technically you have high melting and boiling point. Okay, because you have strong metallic bond. Now remember what is metallic bond? If you have forgotten metallic bond, please refer back to the group 1 element videos. Right, I did a brief explanation on the metallic bond. Okay, now for silicon, okay, you also have high melting and boiling point because of covalent bond. Covalent bond is the bond that exists in the atom. All right, so this one later on you will learn in chapter 5 bonding. Okay, we will go in detail about the meaning of covalent bond. All right, for non-metals, remember, okay, low melting and boiling point due to weak van der Waals forces. All right, so if you see here, the key differences between the elements in period 3 is that when we talk about melting and boiling point, sodium and aluminium, sodium to aluminium, we are referring to metallic bond. Okay, now this one we are referring to the covalent bond between atoms. Alright, whereas for non-metals, they do not form atoms, they form molecules. Okay, so we are using van der Waals forces to explain melting and boiling point for non-metals. For metals or semi-metal, we will use either a covalent bond or metallic bond to explain the melting and boiling point. Alright, so that is the physical changes or the physical properties in period 3. So technically you have 4. Alright, atomic size, electronegativity, okay, physical state, and then your what they call electrical conductivity, and also melting and boiling point. Right, so those are the important things about period 3. Okay, so for chemical reactions, we only focus on the oxides. Alright, so technically we are only going to learn about sodium oxide, magnesium oxide, aluminum oxide, and so on and so forth. Okay, so the most important thing here is that if you notice, okay, you must know which elements are basic oxide, which elements are acidic oxides for period 3. Now, amphoteric oxides. Okay, the meaning of amphoteric oxides is that this particular element, which is aluminium, they can react with both acid and base. Okay, so remember, the meaning of amphoteric is that aluminium oxide can react with both acid and base, or in other words, we call it alkali. Okay, base and alkali are almost the same thing. Okay, so technically, we are going to look at the, technically the first thing you need to know, all right, which one are basic oxides, which one are acidic oxide. Okay, only one is amphoteric, which is aluminium oxide. Alright, so if you are basic oxide, meaning you can react with acids. If you are acidic oxide, meaning you can react with alkali. Okay, so let's look at an example of the reaction here. Now, if I take for sodium and magnesium oxide, alright, if I try and react with water, I'm going to form alkali. So let's say I'm taking this for example, the first one. Okay, so let's say I'm taking sodium oxide. Okay, sodium oxide Na2O plus water. Okay, I'm going to get alkali. Okay, so this one I will be getting sodium hydroxide. Okay, so this is not balanced. My equation here is not balanced, so I leave it to you to balance the equation. Okay, so this is the first example. Alright, so second example here, basic oxide. If I react with acid, I get salt and water. So let's say for example, I'm taking magnesium oxide, and then if I react with, let's say, hydrochloric acid, okay, what I will get is magnesium chloride, MgCl2 plus water. Okay, again, this is not balanced. Okay, you need to balance the equation. So those are the two examples of reactions of your basic oxide. Okay, now amphoteric oxide, meaning I can react with acids and alkali. So in this example, we only have one, which is aluminium oxide. Okay, aluminium oxide. So Al2O3. Okay, if I react with an acid, let's say for example HCl. Okay, the salt that I will be getting is aluminium chloride. So AlCl3 plus water. Okay, again, this is not balanced. You need to balance the equation. Alright, you need to do a lot of exercises. Okay, now the second one. Okay, so the first one is with acid. Okay, second one is with an alkali. So let's say if I take Al2O3 and then I react with sodium hydroxide. Okay, so this one I'll get something special, which is for sodium aluminate. Okay, the salt here is called sodium aluminate. Alright, so this is called sodium aluminate. NaTe. Okay, so this is the salt obtained from the reaction between aluminium oxide and also sodium hydroxide. Alright, and then the last one, which are the acidic oxides. Example, sulfur dioxide. Alright, if I react with water, I am going to get the sulfurous acid. Okay, this is not sulfuric, this is SO3, right? Not SO4. So this is called sulfurous, not sulfuric. Okay, alright. And another example, if I react with alkali. Okay, so let's say if I take silicon dioxide, if I react with sodium hydroxide, alright, I'm going to get sodium silicate and water. Okay, so this particular salt here, NaSiO3, is called sodium silicate. Okay, that is the name of the salt. Alright, so technically those are the chemical reactions for period 3 elements. Okay, basic oxide, amphoteric, and also acidic. Okay, so just remember, if you are basic oxide, if I dissolve in water, you form alkali. Okay, and then definitely they will only react with acids. Okay, whereas for acidic oxides it's the other way round. Okay, if I put it in water, I form acids, and then I can only react with alkali. Amphoteric, I can react with both acids and alkali. Okay, so that is it for the chemical reactions for period 3 elements. Okay, so technically we have two, right? Reactions with water and also either with acids or alkali. So here are the observations. So I'm just going to show you a very short video, okay, regarding the reactions of metal oxides and also the water. Okay, we can look at this one first. Okay, so here they are going to show you the reaction between magnesium oxide and water. Alright, so first thing what they are going to do is that they are going to burn the magnesium strip. Okay, this one I believe that you have done this in your lab when you did the combustion for magnesium oxide. Okay, so technically if you burn magnesium, you will see a white light. Okay, so this is the white light. Alright, and then after they cool, you are going to see white color powder. Okay, so those white color powders are magnesium oxide. So he's going to take some drops of water and then put it on top of the magnesium oxide. Okay, so technically they do not really solubilize in water, only partially soluble. Alright, so when we test it on litmus paper, you will be able to see the changes in the color. So the blue color litmus paper remains the same, whereas the red color litmus paper, you can see that this particular drop right here is turning blue. Okay, meaning that magnesium oxide is a basic oxide. They change litmus paper from red to blue. Okay, alright, so we can look at another one. Okay, alright, so he will be testing the what they call pH value using a pH meter. So as you can notice, when he puts the pH meter into the solution of magnesium oxide, the pH value is more than 7. Okay, it's 10 point something, meaning it's a base or alkali. Okay, so that is the pH value for magnesium oxide. So we know that magnesium oxide is a basic oxide. Alright, next will be aluminium oxide. Now, as you can see, right, the pH value for aluminium oxide is slightly lower. Okay, it's around 9. It's still more than 7. Okay, so technically you will actually call them as basic oxide, right, since the pH value is 9. But in truth, actually, they are considered as amphoteric because when you take aluminum oxide, you can react with acid, okay, and also alkali. Okay, so silicon dioxide, as you can see, the pH value is getting lower and lower. All right. So now it's below 7, so it's going into acidic. Okay, silicon dioxide is an acidic oxide. Okay, so 6.3. All right, not very acidic, meaning it's a poor weak, it's actually a weak acidic oxide. Okay, so those are the few examples of what we call reactions of the oxides in water. Okay, so technically based on the pH value, you will be able to know whether it's a basic oxide or acidic oxide. All right, so this one is a basic oxide. Okay, all right, this is also basic oxide. Okay, and then phosphorus oxide and sulfur dioxide, since the pH value is 3, meaning they are acidic. All right, so this is the reaction between acid and also alkali. Okay, so technically if you are a basic oxide, meaning you will react with acidic, so that is why here dissolve. Okay, here no changes, meaning confirm that this one, magnesium oxide, is a basic oxide. Okay, for aluminum oxide, okay, there's a mistake here. By right, because aluminum oxide is amphoteric, so meaning that you should be able to see changes also. Alright, so for aluminum oxide, can you change the observation to this? Alright, change the observation. This one should be same like this. Okay, meaning the white solid dissolved to form colorless solution. Okay, because aluminums are amphoteric, meaning they can react with both acid and base. Okay, so by right, both reactions also you will see observations. Okay, silicon dioxide, since they are acidic, meaning they cannot react with acid, they can only react with alkali solutions. Okay, so that is why you will see a reaction happening in the alkali. Okay, dissolve. Right. So technically, that is it for the chemical reactions for period 3. We only study about the oxides. Okay, so that is it for period 3. So important thing is the trend, okay, atomic size, electronegativity, and then the chemical reactions. Okay, so that is it for today. See you again soon.